We need to review the evaluating and graphing of piecewise defined functions. And so the problems that you've been assigned sort of tackle both of those all at once. Basically, you're given a piecewise function, like here we have g of x, and it's defined over the domain. There are two parts to the domain, right? For x is less than -2, we follow the rule where g of x equals x. For x is greater than or equal to -2, we follow the rule 1 plus the square root of x. And in each case, I've given you a blank table of values where I've provided the x coordinates, and I want you to evaluate the function and provide the y coordinates. You'll notice in each of these tables that transition point occurs twice. And the reason for that is when we're graphing, we need to know where the solid dot goes and where the open dot goes. And what I mean by that is you'll notice that g of -2 is only defined in one place, and that's on this second rule because of that less than or equal to. But up to and not including -2, we're defined on the left side. So we need to know where that thing's heading. I'll show you what I mean in a second here. But basically, left of -2, we don't use that top rule. Let me say this in a different way. The top rule we don't use to evaluate g of -2, but we do get close to it if we're at -2.1, -2.2, and so on. So on the graph, we indicate that with an open dot. In the bottom, where it says x is greater than or equal to -2, we do use a solid dot for that g of -2. It'll become a little clearer as I fill these values in. So let me just go ahead and do that. To compute g of -6, I'm going to use the top function, which is g of x equals x. So y equals -6. And I'm going to plot -6, -6 here. And then same thing with -4. G of -4 is -4. And I'll go ahead and plot that point, -4, -4. Now, I want to indicate that we go up to but don't include -2. So I'm going to compute the value, but I'm going to put an open dot there following that rule. And in this case, g of -2 with the open dot is just going to be -2. And I will indicate that with an open dot there. That point, that y value, is not g of -2. But all these other y values here to the left exist. Now moving down to this part of the domain, starting at -2, I need to evaluate the function 1 plus the square root of x. Now here's the problem. When I plug -2 into that function, in the real numbers, that's undefined because I can't take the square root of -2. So there is no solid dot for this particular point, even though I was intending to put one there, because this function is undefined at -2, at least on the real numbers. When I plug 0 in, though, I do get a square root. The square root of 0 is 0, so I can do 1 plus 0, and that y value is 1. So I can pick up here at 0, 1. There's just no points between x equals -2 and x equals 0 for this function. That's all, because of the way it's defined. I can take the square root of 1, so when I plug that in, I get 1 plus the square root of 1, which is 2. So 1 comma 2, which is there. I can take the square root of 4, which is 2. So 1 plus 2 is 3. So 4, I'm at 3. And then this function, it's shaped like a square root function, just shifted up 1, takes off like this. And so this is a sketch of the graph of the piecewise function. Don't freak out that there are two pieces. There should be two pieces because we have two rules. We have y equals x for the section here between -infinity and -2. And we have y equals 1 plus the square root of x for all the numbers greater than or equal to -2 The problem is we can't start using those numbers until we get to 0 because we won't be able to take the square roots. So that's this piece over here. And then it's okay that there's just this gap in here. Those numbers are not part of the domain. Okay, so that's the deal. You fill in the y column by choosing the appropriate rule to evaluate the function, and then you plot those dots and sketch the curves. You will always have, at that transition point, two calculations to make, one with an open dot and potentially one with a solid dot. In this case, we didn't get to use a solid dot because the function is not defined at x equals -2. Let me show you one more example. So here we have another piecewise defined function. This one won't have any undefined values because we can raise any real number to the 5th power. So we should be able to evaluate all these. Let me point out that we do have a transition point, right, at x equals 0. That's why I've indicated both of these. Again, this top 0, because it says x is less than or equal to 0, this is going to be my open dot. And this bottom one is going to be my solid dot. So all the numbers less than 0 follow the top rule. So -6 minus 1 is -7, and we'll plot that point down here at -6, -7. -4 minus 1 is -5, and we'll plot that point here at -1, or -4, -5, sorry. -2 minus 1 is -3, and that point is here. And then this is going to be my open dot. 0 minus 1 is -1. So at 0, -1, there's an open dot. And that function takes off from here, just very similar to the way the other function took off. From this point forward, I'm going to use a solid dot, and I'm going to follow the bottom rule because all of these numbers down here in the bottom of my table are greater than or equal to 0. Okay, so when I plug 0 into this function, I get 0 minus 1, which is -5. I'm working right here. And -1, not -5. 0 minus 1 is -1. When I raise that to the 5th power, I still get -1. So I'm going to have a solid dot at 0, -1. So that solid dot trumps that open dot that I just put on here. So I'm going to remove that, and we'll just put a dot here now. So there is a solid dot at that point, not from the left rule, but from the right rule. Let's try w of 1. When I plug 1 into the bottom function, because it's greater than or equal to 0, I use the bottom function. I get 1 minus 1, which is 0. 0 to the 5th power is 0. So that's here. 2 minus 1 is 1, and 1 to the 5th power is 1. So that's here, 2 comma 1. And then 3 minus 1 is 2. 2 to the 5th is 32. Holy smokes. So once we get out to 3, we are off. We're off the chart here. And what I know about a function that is an odd power is that it has a shape something like this. So essentially what we've got here is this thing, and it just takes off. So just kind of be careful with what's happening in here. It's going to have this shape. It's not just a straight line up to that point and then takes off. It's curvy, and it has that interesting shape where it starts like this and then it levels off and then it takes off that way. That's how these odd powers look. The parent functions, a cubic, a 5th root, a 7th root, they have that shape. All the even power functions, just to remind you, all the even power functions look like a parabola. So x squared, x to the 4th, they just flatten out a little. X to the 6th, they all have this shape. But all of the odd powers have this shape. So again, I've evaluated. How did I miss -2? What was the answer on that one? That was -2, -3. I just didn't write it in. I evaluated by plugging these numbers into the appropriate rule of the piecewise function. And then I was careful when graphing that transition. In this particular case, these two pieces of the curve touch at 0, -1 because they both had the same y value. Sometimes that doesn't happen, like we saw in the other one. There's a gap or a jump in the graph. But in this case, there's no jump. This function is what we call continuous, right? It touches everywhere. But that's the idea behind graphing and evaluating piecewise function. We figure out some y values, and then we sketch the graph in. Your pictures aren't going to be perfect on these. Don't panic. If I wanted a perfect picture, I just ask you to type this thing into Desmos and have the computer draw a nice picture for you. And we have studied how to do that, so don't be afraid to use that as a backup if you're having trouble drawing this picture. The evaluating part, you just plug the number into either the top function or the bottom function, depending on where you are in the domain. Okay, this video is long enough. Good luck with the review, and we'll see you soon. Take care.